This is the recorded panel discussion at the 2023 International Conference on Compiler Construction. The panel was held on February 26, 2023. It drew a large audience. The room overflowed with people standing at the back. We released this video to further inspire the community and to keep the conversation going. We were honored to have 5 distinguished compiler experts on the panel, including Saman Amarasinghe, Albert Cohen, Chen Ding, Sebastian Hack, and Mary Hall. The moderator was Xipeng Shen. The original video was recorded by Andre Lotek. The topic was on how would compilers change in the next 10 years. First, the moderator clarifies the scope of discussion. Compiler in the topic question refers to processing programs that analyze, transform, or execute inputs that describes how a system operates, including traditional compilers, runtime systems, programming tools, programming models, domain-specific languages, and so on. The moderator then explains the purposes of discussing such a broad topic. It is to motivate the community to think about the trends and the big picture, stimulate conversations on the future of the compiler research field, bring out important research opportunities and directions, and discuss priorities and promote disruptive or revolutionary advancements. The moderator then gave a brief introduction of each panelist. Saman Amarasinghe is a professor at MIT, ACM Fellow. His research focus includes high-performance domain-specific languages, optimizing compilers, and auto-tuning. Albert Cohen is a research scientist at Google. His research focus includes parallelizing and optimizing compilers, machine learning compilers, parallel and synchronous programming languages. Chen Ding is a professor at University of Rochester. His research focus includes locality theory and optimization, memory management, high-performance computing. Sebastian Hack is a professor at the Saarland University. His research focus includes code generation, automatic vectorization and parallelization, compiler design. Mary Hall is a professor at the University of Utah. Her research focus includes automatic performance tuning, interprocedural analysis and optimization, parallelizing of compilers and optimizations. The moderator then asked each panelist to give a 4-minute statement of their views on compilers in the next 10 years.
My conjecture is compilers haven't changed that much at all. Forget 10 years. I am thinking about when I was in graduate school 35 plus years ago. Though, to give you an example, those days, if I talk to an NLP person, we all had a similar kind of structure to what we worked on. Single-threaded process running on your machine that takes some input, converted into an intermediate representation, had multiple phases, and produce output. That's what we did in NLP. Today, you look at something like a Siri or Alexa, you won't even recognize the relationship between the current system to what they had there. You look at a compiler today, it's the same damn thing. It's the exact same kind of thing that happened before. So what's the problem with that? The problem with that is if you look at production compilers, they are very conservative. Given that process, given how we run it, they are very worried about runtime. They are very worried about degrading performance. So even though we as a community has written hundreds of papers for cool compile optimization, none of them are in production compilers, especially turned on by default. So what that means is if you go to a community like PLDI, they will say, look, compilers don't have that much impact. So we don't want to accept your paper. So this is happening at this point because all these things never end up in practice. We need to change this entire thing. We really need to go and rebuild our compilers. So what do you want to do? I want to make compilers go into the cloud. Why? Because then runtime might not be that much of an issue. When I have scalability at the elastic way, I should be able to run a lot of more complicated, interesting analysis in there. You asked me how do we pay for it? There's a lot of redundancy. Lot of things running on cloud, deduplicates, because many people don't do the same, don't do different things. They do the same thing again and again. We recompile same things again and again. So by deduplication, you can actually spend a lot more cost than and amortize it across multiple people. Other thing is, we want to use machine learning in compilers. It's really hard because when you release a compiler's application, you have no access to data. So you can't train the damn thing because you train on few data sets you have, you release it there, and everybody is going to complain because their data doesn't work. How does cloud help? You see everybody's data coming through. So you can train on everybody's data. You can be a lot more receptive to everybody. So I think if we go about that path, I think we will be able to get a lot more interesting ideas, lot more things that we think today not practical into a common compiler base that everybody uses, and do things like machine learning that today is very hard to put it into a mainstream compiler, into these compilers, because the compiler will see what people are doing and can optimize. I think if we go down this path, even right now, I feel like the premier programming language conference like PLDI doesn't respect the kind of performance optimizations the traditional compiler people that got those compilers started. You can't blame them because the things we do so far are not having practical impact. So we need to get to a point that the things we do, the research we do, end up with that everybody else is using, and we need to get there. Let's stop there.
Yeah, that's great. So yeah, that's wonderful. Let's move on to Albert.
Thanks. I mean, I couldn't agree more with the premises. I don't know if the cloud is going to solve all the problems, but it's definitely one thing that we have completely missed. My revolution we've completely missed. So my point is twofold. First of all, I would say that compilers have failed to be accessible enough to a large crowd of software developers, and we have some pride. We take some pride of this. Even we say, well, the students who actually take compiler courses, they are the best students, and we are very happy about that. But okay, it's not enough. I think we should go beyond that. We have consistently be ultra selective on the barrier of entry for compilers, and I can say a bit more later. The other point I'm making is I think the very big challenge right now is that after so many years of taking compilers for granted, people are really opening the box of the compiler to do things that are typically we would expect would be done by a compiler that is typically a black box. Let me explain. I'm from the performance optimization side, of course. If you want to optimize to death for a particular domain, the typical answer has been, oh, write a domain-specific compiler, domain-specific language, and optimization heuristics. You have all the abstractions you want, the static information you want, etc., and even you can train your heuristics on that particular domain. So it took many years actually for industry to take over, to take that idea, but we are there. That's where we are now. But it's not what people do. If you look at Halide, if you look at schedulable compilers, if you look at interfaces like MLIR, which is primarily a toolbox for building compilers and building infrastructure that process software, the whole point is that there is no source language, not even the DSL. There can be any source of any form. It can be even an NLP framework. It doesn't have to be any well-defined formal language. It can be just an API. And then you open the tools for developers to implement some kind of custom flow, custom path within the DAG of transformation passes and analysis. And that's what people want. They actually want to have total control on what the compiler does. And I think this is primarily this is a risk, first of all, for traditional compiler research and engineering, because we have kind of left that way of doing things for a very small niche of compiler constructors, which are here, and very few experts. But now we are going back to the first point. We are opening this need of having tools that can actually construct compilers for very specific usage to a very broad range of domains and users. And once again, we have failed, I think, on that front. So it remains very hard. So people want to do it. There are great examples of, let's say, schedulable compilers, controllable compilers, where this has met success. But how do we make it possible for any expert of any domain to actually do that? That's my main interest.
Excellent. So next, let's move on to Chen Ding.
So my interest and my decade's work is really about memory systems. So I would say a little bit what I think next 10 years about programming the memory hierarchy. So my hardware, of course, memory is all becoming more complex. We all know that. But what about programming? How do we tackle that? If you think about program, it's really a formula of computer operations. And today, really glad Mary gave the talk. What her students lost is Oregon. It's about what is locality and why is it difficult to optimize. And one thing I remember Mary explicitly mentioned is the input size. That may not matter much to CPUs, but to memory, that's a big difference. And then the analysis we do, one is symbolic. I want to say that next decade, we're going to go one step further. It's going to become a simple topic. So I want to say just a little bit what I mean here. So we measure the cost of memory system. We actually don't have a way that's symbolic and sympathetic until we now have the recent work. My co-author Wesley Smith is sitting here. We call data movement distance. Data movement has been talked about. This is really put a unit to say what is data movement distance, and once we have that, but it's not a unit of work of CPU. It's really a unit of work for memory. If we look at the memory, the most effective algorithmic improvement, cache-of-Libis algorithms. So you just have to use it if you want high performance. There is actually no difference in time complexity. So what is optimizing? So Wesley Smith's paper in ICS last year shows that it actually reduces data movement distance asymptotically. Then why not using the cache complexity analysis that cache-of-Libis people already use? So compiler people are practically minded. We're all here. It's not if you just give me a theory, I'm not necessarily interested. So if you tell them, if people tell us use time complexity, we'll say, we know the cost is memory, not CPU. If you say cache complexity analysis, how many of you know that actually? and then it's big O notation. And in big O notation, constant factor doesn't matter. The minute you say constant factor doesn't matter, that's a big problem in practice because our optimization is improving. Constant factors be great actually if we do. So in data movement complexity that we have, constant factor does matter. A factor 2 means the difference between a one-way and wrong trip. So that's the very quick introduction of that concept. So the idea I think we can do to make compiler more effective is to address the issue of memory systems going beyond symbolic analysis to a sympathetic analysis. Now, finally, to address Saman's point, how do you make people adopt your new ideas? Let me just say this, that if I can reduce the memory cost sympathetically, people will pay attention.
All right, thanks, Jen. That's great. So next, let's move on to Sebastian.
All right. So I work at a German university, and I'd like to take that opportunity to share with you maybe a bit of German melancholy, maybe also German romanticism. Let's see. So I did my PhD in 2006, and since then, this has been a long trip of understanding what actually doesn't work at all in compilers, and the list gets longer and longer. So it's many things don't work. So some things that I'd like to mention, and then maybe also comment on maybe future directions is the following. So when I started research, I was super excited, proving properties about certain things and proving, I don't know, complexity about certain compiler optimizations and so on and so forth. And that was all nice and shiny. And then I realized, okay, some of these problems are actually very hard and they're incomplete. And then you start with kind of solvers and try to come up with optimal solutions. And then I understood, okay, so maybe it's also important what kind of cost function you have. that you're optimizing towards. And then you realize, okay, if you write simple heuristics by hand, they often produce faster code than what these optimal techniques spit out. And then you start wondering, oh my God, what's happening there? How can that be better than optimal? So and I guess what the point I'm trying to make with this is, if I look at something like LLVM, which is an incredible, incredibly well-engineered and well-done piece of huge and complex software, it's just a wonder that it works. But it's also impressive how good the quality often is, and it's also impressive how good the quality of the code sometimes not is. And the reason is that we don't. It's not about the people who work on this, and there's also a code of myself and students from myself that are in LLVM. So I'm not blaming people. The thing is we have absolutely no proper models of the machines that we are compiling for. The abstractions that we use for the hardware are so super simplistic. It's actually a wonder that maybe it's because of hardware architects, because they are able to design the sophisticated hardware around the, let's say, the failures of the compiler people. So, and by that they create so complicated hardware. It's even more hard for us to model. So I think there is maybe it's a kind of vicious cycle there. But so my point is, it's really hard to have a precise understanding of the machine that you're compiling for, and it's, I guess, even harder to have algorithms that are able to read the machines that we are compiling for. So sometimes I have the impression a compiler is something. So I'm not playing golf, but that was the first analogy that came to my mind. It's something like a golfer that puts the ball on the green, and then the hardware puts it into the hole, so to say, right? So, and this is, from an engineering perspective, unsatisfactory, because I often have the impression when we do this backend kind of code optimization things, we don't know so much what we are actually doing, because the knowledge of the target machine is very weak that we have. So that is one aspect, but it doesn't get better. So the other point that I'm trying to make is, apparently we are able to work with infrastructures that are formally heavily underspecified. So we have huge code bases, and people rely on these compilers as well. And as far as I'm concerned, not many, but some aspects, some corner cases in compilers that we use are still not properly defined. And by properly defined, I mean in a formal way. We compiler people seem to be very good at creating huge artifacts that can do amazing things, but we also seem to be able to ignore the fact that we actually don't know exactly what they are supposed to do, because we just don't care about having formal specifications of all the languages that we are using. And I think what we need to do is whenever we come up with a new thing like NLIR or LLVM at the time and so on, we also need to start working on formal models that precisely describe what the programs that we express in these languages do actually mean, so that people can come up with correct optimizations and transformations on these things.
That's the question. Yeah, that's great.
That's it.
Yeah. We have more time for you to give your opinion later on. So yeah, Dr. Merithoff, please.
So I get to be last, and so I'm gonna kind of rip off what other people said. I, along with Saman, were toiling away, building compilers 35 plus years ago, as he said. And you know, at the time, so this is the 90s, at the time, we believed we could automate everything. I mean, we really believed we could automate everything. And the hardware people were the same. They believed they could automate everything as well. So we're not the only guilty party. And so we built compilers where the idea was, you know, so we were building compilers that took sequential code and generated parallel code. And we believed, we believe the programmers shouldn't have to worry about that. It's too complicated. You have to understand the architecture. You know, we'll take care of it. Don't worry. And so, you know, the compilers at that time, they had passes. I mean, you still see passes in compilers, but this idea that something happens, it has an input, it has an output, it's transformed the code, but it's still equivalent to the previous code. And you're just going to run a bunch of passes. And in fact, you know, we don't know which order to run them. So we're just going to keep running them over and over again and see what converges. And so within those passes was a bunch of code that somebody wrote, or maybe a small group of people wrote, and mostly no one understood what was going on inside them. And so they just never wanted to touch them. And I think that's kind of getting directly to what Sebastian was saying. So, so I've been working in high performance computing, you know, pretty much my whole career. And so, this gave compilers a bad name because, you know, sometimes, I mean, we did heroic work at Stanford and we could get great results on very specific things. But if something was broken, you know, some little thing in the code, the compiler didn't understand, you were doomed because we were trying to get coarse grained parallelism. So, so this gave compilers a bad name, and then people had to figure out how to use compilers, because compilers are really great at certain things. Like they can generate code that is very hard for programmers to write themselves. And so we went to this period where we were trying to expose interfaces that allowed programmers to use the capabilities of the compiler, like really good code generation, pretty good, you know, vectorization, you know, a bunch of things that it was good at doing, and expose the things it wasn't so good at doing, the things that were fragile, the algorithms that were hard to piece together. So that led to things that, like the session right before lunch that I was, you know, a participant in, the idea that we're going to expose interfaces in the compiler for experts so they can write really fast code without having to generate the code themselves. And we got into domain specific frameworks so that we could concentrate the optimization strategies on very specific domains. And, you know, we got low level programming models like CUDA, for example, that are exposing the hardware execution model so that you could write code that could, you know, without a bunch of things in the middle that could generate, get good performance. And so, so I guess my story for like what I think is already happening now, and I think is sort of a direction I'd like to go, is let's go back to trying to automate everything. And so now we have, why is it different? Well, it's different because a lot of things are automated that we would never have thought could be automated. But it does mean that the compilers have to look different. And so, so one thing is we have to keep responding to hardware changes. And so we need compiler infrastructure that can do that. The kinds of things we were talking about in this morning session, both in Vikram's talk and then the session right before lunch, is things need to use abstractions that take the programmer out of the compiler developer out of the middle of the loop, and so we don't have these kind of problems. I guess I have to wrap up. So more composition, better abstractions, more synthesis, more machine learning. And, you know, something that is a big focus of my work now is data layout as a first class thing that the optimizer that is exposed to optimization, because data movement is the fundamental barrier to high performance. So I'll stop there.
Great, thank you very much. Well, thanks for all of the panelists. That's an excellent summary about the opinion. Now we start getting to the second session about Q&A. I'll start with some prepared questions first, and then we'll open up the floor for everybody. Now, I think some of your summary already covered some of these prepared questions, like what has been the kind of barriers for development of compiler. But I still want to ask the panelists, maybe you can concisely summarize the top 2 critical challenges that we are going to face to make compiler more effective in the next 10 years. Top 1 or top 2 in your mind. We'll just go around. Everybody have the chance to say that. Top 1 challenge that you feel like the community will be facing in advancing compiler for the next decade.
Top 1 or 2.
Both one, yeah.
So say, oh, dude, I think data movement optimization is one, and then I actually polling my colleagues about your question. The first thing people mentioned is actually, Mary, you co-authored a paper, compiler future for next 50 years
Mhm.
in CATM.
Mhm.
You wrote that 10 years ago.
Yeah.
I think a lot of other feedback is actually usability of the compiler that many of you are touching on. So I'll say that's also one of them.
Yeah, I wish I remembered what was in that paper, but I do remember it talks a lot about automation, about these sort of abstractions that allow automation, but probably in a different way. Yeah, so I mean, I close with data layout. I think that we need to automate the composition of data layout with code optimization, code generation, and code optimization. We need to build that into our compiler infrastructure. So that's one of the things that I think is important. And I think, you know, getting to like looking at machine learning infrastructures and why are they so successful, you know, these compilers and tools and code generators, it's because they have different layers of abstraction, and people who are comfortable with those different layers can enter the system in different places. And so there is an ecosystem that a lot of large amounts of money has been thrown at to build those systems. And so, you know, we need to build the same kind of ecosystem that's not just about machine learning to solve other problems.
So what I would say is compilers needs access to data. Not just for machine learning, but if you eat your own dog food, it gets much better. And a lot of times we build compilers for others, and without access to data, especially modern like machine learning type stuff, it's very hard to do. And if you look at the companies who have been successful in using machine learning, they made sure they have full access to all the data of where their systems is being used. So we need to make sure the compilers, the way we do is doesn't work. We need to come up with methodologies where we get access to data of all the people who use the compilers.
I'd like to come back to something Mary just said. So I think what I see is that there are more and more different programming languages or little languages that people want to use because of the problem that you cannot get performance out of general purpose languages anymore. And there's also more and more domain-specific hardware. So people have the urge of creating or needing an infrastructure in which they can embed and embed their own little languages and maybe also code generators into. And of course, there are movements like MLI and so on who try to address this. And I think we need to carefully figure out where a sweet spot is between an omnipotent thing like MLIR, which is a very generic, in my perspective, very generic representation of programs, and something that is maybe a bit more restricted in the sense that you can give it a semantics and that has maybe also well-defined constructs and maybe also sort of something like a type system and so on and so forth, that you actually can use this as some kind of nucleus programming language. I guess this is a recurring theme in compilers for decades, right? In the 60s, there was this unfold movement, I've been told. I haven't been around at that time, so I think that is a problem. That's a problem that doesn't go away apparently, and maybe we should. That's fine. Yeah.
Thank you. Yeah, I think just continuing on that. For decades, people have worked on static analysis first, syntactic analysis, and then static analysis, semantic analysis, and so the heroic efforts that the Stanford group was dealing with was largely about that. But maybe that's not what compilers do best. I mean, there's this whole field of verification and static analysis, etc. But what people really expect right now is robustness. People want compilers to deliver, to do a good job, where they expect they should do a good job. Like some optimizations, like scalar optimizations, like constant propagation, etc. I mean, we don't even think about those anymore. It may not be optimal in Sebastian sense, but it's pretty good. So I think we should focus our efforts on where compilers solve problems that are well in the scope of what compilers can do in terms of optimizations at least. And having said that, it probably means two things. One is so formal guarantees and specifications was mentioned several times. if we want to do any type of synthesis, if we want to get any strong robustness, predictability, warrantability, however you want to call it, guarantees, you need that. And definitely MLIR is not something that is amenable to be formalized. It's way too much of an API, it's a software engineering infrastructure compared to a programming language. So you need some sweet spot. I fully agree if you want to achieve that. So we want focus on what we do best, focus on formalizing that core. And one thing I keep on insisting upon for many more than a decade is it's also a self-serving effort. I mean, competitors will very much automate ourselves out of business. So, and we should continue doing that. And I think we have slowed down the pace of doing that, especially for the reasons I was mentioning earlier. Like we are providing toolboxes, we're doing all kinds of things for others to write more specialized compilers, etc. But I don't think the core principles have progressed as much in terms of automation of building compilers. So there have been a few, like Bigram's, of course, it was about that. I think we should put much more emphasis on making our lives easier as well.
All right, thank you very much. So now, well, those are all excellent points. Now we will open the floor. I'm sure lots of questions are waiting there.
Okay, so
we have one mic.
So a number of the panelists are talking about more success in using machine learning for compilers. And I want to ask a question about how well are we doing as a community in the rigor in which we use learning in compilers. We know that we have a very patchy history. CGO is starting on Monday, and if you look at CGO papers from 10, 15 years ago, you're going to see this single point of evaluation, single point of training, and calling this, profile guided optimization kind of thing. And we know that the issue of characterizing behaviors of programs and such is a very difficult one. And especially considering that we are changing the program as we are optimizing, and our measurements are stuck somewhere in the past. And I think we are all familiar with a number of issues that we have had in the community. So my question is, what should we do about the rigor, not only on specifying languages and such, but the rigor on using learning and using data?
So there's two parts to that, I think. Lot of machine learning, what we have, at least we have done, is not going into the correctness aspect of the program. So you are trying to do basically heuristic parts of the program. So if you look at a lot of heuristics that inside current compilers, they are atrocious. Lot of these we find heuristics with silicon graphics based written for SGI ART8000 that still were trying to use today. That all of it. There are a lot of old stuff in here. So part of having some machine learning is to at least modernize it. If you have good cost models that can learn every new architecture going forward, it will at least be somewhat representative. Obviously, we need to have a lot of good data. I mean, that's the problem we have because we don't see most people's input programs. And so we train on our program and then we give it to other people and everybody complains that their program didn't work because you need a lot of data. If you go beyond that, when you want to step onto the place where correctness and issues come out, you have to be a lot more careful, you have to be a lot more rigorous. NLP, if you get a sentence a little bit wrong, people will be okay. Not in compilers, they expect, unfortunately, the output to be exactly correct. And so that part, and again, I think if you got machine learning, we are working on a community that's still also struggling with that. Somebody says machine learning is alchemy, it's not science, because it could result, but we don't know why. And things like ChatGPT, what they were able to do is kind of blows my mind, but I have no idea, and nobody has any idea how it's doing that. So we are kind of working a little bit with fire in that sense, but I think it would be, I don't think we want to step away saying, okay, wait until somebody really prove all the properties are there. So we have to go there, but we have to do that with very eyes open, because part compilers is there's this kind of expectation that we don't violate certain things. So that means we need to play that, we need to come up with a boundary. You can't give a neural network, give the input program and translate assembly. That would be beautiful if we can do that like in NLP, but that will, most of the time program will, sometimes it won't, that doesn't happen. So we need to find, we have to have a lot more nuances when you use data. That also, we need to be a lot more data to be a lot more general in what you're training on.
Excellent. Oh yeah.
So I think this panel is a little bit biased.
What direction?
I think you are all experts. And I think there are other roles of compilers that are actually becoming much, much more important. Because there are large communities of people who are trying to use computing virtually for every single domain today, most of whom have little programming experience. And I feel like another big role for the compiler community is to make it much easier for people to write programs without being programming experts. And I think that enabling programmability with high-level specification techniques, generating compilers for domain-specific, whether it's formal languages or natural language or whatever mechanisms, but those kinds of compilers, I think, are going to be crucial, and they are, I would hope, they might build on top of traditional compiler infrastructure, but I think that there's a whole other stack of techniques that need to be built on top of those traditional infrastructure, which are more domain specific and also deal with higher level query interfaces, and maybe even are automatically generated from the high level specification. But to me, that seems like another important direction for the compiler community. And I'm sure that you all have thoughts on that.
Since I came to grab the mic, I can keep asking. So I think the part of that is, I feel like the community is divided two sides. So there's the interpreter type community that you're talking about, that if you don't care about performance that much.
Wait, I don't say that.
Okay, but I'm saying even like think at Python, they care about performance to a certain extent, but they care about other things also a lot more. And they have created a huge amount of interesting infrastructure, interesting methodologies of doing that. I think I agree with that we have kind of kept there's a wall in compilers, and okay, this is the hard part and everything is easy. If we make it a little bit more seamless, so get a little bit like, for example, tomorrow we have a talk on how to make Python compilable. So get to do those things and also make it easy to build domain-specific languages in these kind of. I think we have, the way I look at that is compilers bring some lot of nice, interesting, rigorous parts to it. The people who get trained as compiler writers go to a lot of amazing things because that has got rigorous training. But also we bring a lot of rigor, lot of very good methodologies in here, and using that to apply to some of these communities to be very good. But I agree with you that we have kind of kept some of these things as it gets inside.
And I do want to say, I think performance is very, very important in any of those. Find ways to deliver both programs.
Yes. Yeah, I would say that you can get performance without compilers in the code, like low-level code generation sense for most of these languages. For example, Python usually doesn't use a compiler for getting performance, it just uses code that has been pre-generated or even written by hand in the library. And I think that's a point I also made at CBC recently, but I think this, what you were referring to as blurring the lines, basically, is very important. So we should focus on what we do best. And like trying theoretically to compile Python is not what we do best. I mean, it's you can change Python, but probably you won't get any programmers anymore using that subset. Yeah, but there are lots of embedded DSLs.
Yes.
So, and those you can focus on, and those you can decide also what gets interpreted, what gets compiled. You can even use the data from the actual runs, from the actual users, if you have access to it. Another question, to decide what's going to be interpreted, what's going to be compiled. And right now we don't have the infrastructure for doing that. Either building the compilers that can make this decision about compiling or not compiling based on data on, and even less about actually deploying it next to the data that can help take those decisions. And actually very much in the spirit of early days of CGO, which was, and I know this is not CGO, but still, having like profile-driven information, but the actual data, not just some benchmarks, was like lifelong optimization, etc. Of course, this was in the air for a long time. Probably now we can do it.
All right, thank you. Yeah, more questions? Yeah.
So, my computer architect, well, I'm really surprised that there is no more focus on the AI. And from a hardware point of view, now you have 10 to 100x speed up, just multiply, you don't want to use AI. So you can change a lot of the algorithms, you can rework. The hardware is going to bring you there a lot of capabilities you didn't have before, because there is a big focus on the AI. And you can rework like transformers everywhere inside the flow. And if not, just metric multiply in your algebra. So what do you see there? Because I thought it would be more like a boring panel saying, yeah, AI, everybody. Like what we are doing in hardware, a lot of focus.
Come on, 2023. That's the word.
Yeah.
Well, I guess I was a little confused as to whether you were talking about using AI in AI support in the hardware to solve
It
problems.
mostly that the hardware is going to be there, so you can change your compiler and leverage that
Yes.
to have huge speed ups in your compiler infrastructure. Maybe you still compile C.
Well, so but we do.
But I'm saying you have a lot of different substrates.
Yeah, so we do like the whole thing about compilers for high performance computing is tracking what the crazy hardware ideas are at the moment. And I mean, now those and being able to optimize for them. And now those.
It's slightly different. Like, listen, give me an example of imagine you have Raster allocation. What you use a crazy matrix multiply to do Raster allocation?
Oh, okay. Now I did not understand. Okay, well now somebody else probably should answer.
So this is something I complain a lot, because we as a compiler community is in the center of using a lot of new hardware. But if you look at a compiler, it doesn't even use a darn GPU. No compilers have used even parallelism is very rarely used inside a compiler. So part of that is we don't eat our own dog food, and that's really bad. And I think there are a lot of opportunities in the compiler. We don't even use frameworks. I mean, a lot of other systems are built out of other frameworks. We just basically spin our own thing from scratch, and we stick to that. And I think there's a lot of opportunities, new hardware, cloud, all those places where compiler itself can be thought a little bit different. Like, for example, a lot of areas went to cloud and graph framework. We say, oh, we can't do global analysis because it's too expensive. What the hell? I mean, there are people analyzing huge social networks that are so much more bigger than any program that we can do global analysis for. Why can't we use all these frameworks? There's a lot of opportunities there that I think compilers should take on. Thanks for that.
Right. Do we have anything to add to this?
I guess it's fine. We don't have solution.
All right. So let's see. Do we have any other questions? No.
I just asked one specific question about we are looking for some new compile technology to help this traditional compile. One is of course using machine learning. Okay, but using machine learning now we face some challenging about is what machine learning can help the compile optimization. For example, today this morning we talked about the interchange. From traditional point of view, we pretty much know the performance model for this loop interchange. We just look at based on architecture, we know that continuous access is cheaper than the strata access. So pretty much the simple model can do that. But now the general is, I just ask some kinds of opinion advice what machine learning could help this compile.
Very briefly. So you mentioned mostly, I mean, I agree, of course, this is a great challenge for the future. But already ML is using compilers for auto-tuning, for building heuristics that plug into existing passes to replace like analytical models with learned cost models, etc. So this is kind of commonplace now. It should be much more than that, but I think we should go way beyond that, and most likely that's what other panelists have in mind as well. So automating ourselves out of business really means like more like synthesis, more like learning automatically which analysis, which features, or not even features, directly learning representations, and how to transform the code, how to generate code that achieves a given goal that's defined as an optimization problem that ML can solve. The problem is how to do that with soundless branding, how to do that while also preserving semantics. So if you have a formally defined IR and at different levels, you can get started on solving that problem. But it remains a very difficult problem that ML typically doesn't solve well, except maybe reinforcement learning, which can more easily be combined between optimization and like an agent that actually navigates within the soundness defined space. I'm actually going to talk about that for register allocation later on, just readvertisement. But I think that's more where we should go rather than just tuning existing neural.
If you look at the areas that have been very successful in machine learning, they came up with a good embedding for their data. CNNs became a really good embedding for images, transformers became really good embedding for natural languages. And once you have good embedding that captures the information of what your domain, then you can do a lot of really cool magical things. We still don't have good embeddings for programs. The programs have syntactic information, but there are also deep semantic information that's important in there. The embeddings today that are using like natural language can capture the syntactic information, but they don't capture the semantic information of the program. So if you try to learn for programs, we miss a lot. So someone who can come up with a really good embedding that captures both syntactic and semantic information of programs can take machine learning to the next level in compiler.
Yeah, a little thing to add. I mean, I guess many of the interesting optimizations the compiler has to do are just very hard, and this is the word I'd like to emphasize: combinatorial optimization problem. So, like an integer linear program and things like that. And so, if you think about learning in that context, it essentially would mean that you need a large base of data where you have solutions to combinatorial optimization problems. Problems just that they are all NP-hard, and solutions for getting solutions for them is super difficult, right? So it's very difficult to train on something basically because you don't have so many solutions. So I guess a big challenge is to leverage learning techniques to solve combinatorial optimization problems, because this is at heart what many or most of code generation and optimization problems in compilers are.
All right. Well, I'll ask the panelists one question. Actually, this is follow-up question following the Vikrant's question. We have been mostly talking about performance. Vikrant mentioned the productivity, but besides these, there are also other goals people care about a lot, like security, privacy, in computing. There are lots of work actually already using compiler to analyze code, to insert, to add, to improve security of programs. How do the panel really feel about these different goals in terms of the usage of compiler, and will there be some kind of synergy with performance? For sure, there will be, but what kind of suggestions you guys have in mind?
Well, since I have the mic, I shall say. Can I give it to you?
No.
Yeah. So one quick comment that I want to make is, I think if you what you have in mind is maybe things like mitigations for sidechain attacks like Spectre, or ensuring constant time runtime of programs. So the runtime of a program is independent on secret inputs. Is what you need for cryptographic routines maybe. I think you can do this only if you have precise formal models of what the programs mean that you have, so of your IR and the assembly code, and in addition the microarchitecture of the machine. All these things don't mean anything if you don't have a formal model of the microarchitecture of your processor, because you need to formally say what a side channel actually is, and you can do that only if you have a formal model. So that is my point of that.
I was going to say something similar, but let me say it a slightly different way, which is all the things, the layers of abstraction that are composable and their interfaces, their interfaces are exposed and well-defined and formally defined. I mean, all of those things which also allow us to compose compilers together quickly and without all of this, fragile stuff that we've been dealing with for a long time. All of that will make them more, not only will it make it easier or generate faster code or support a broad user base. They're all fundamental to all of the questions that we're talking about. And so they'll also make things secure.
So if you look at compilers, there are two big parts. One is analysis, and one is transformation. Analysis is all about trying to understand what the program is doing. And if you want to do all these things, security, all these other parts, first you have to understand what the program is doing, what's in there. So a lot of the things, analysis we do will be useful for very large domains. Even things like explaining the program, explaining the bugs, or these kind of things also, the kind of analysis can be useful. So in some sense, a lot of things we do are very general.
On the other side, that what Saman said, that the compiler techniques can contribute to the solutions. It's actually the also problems. If we think about correctness, the biggest correctness is the problem is actually because we optimize for performance. Sebastian mentioned the example that I see a hardware parallel to side channel attacks. It's really because architecture were there to optimize performance. That creates the correctness problem. So such an excellent question, but I think there's maybe even though we're going beyond performance, look at that problems, but I think performance somehow, I think is, if correctness problems is any guide, is the performance still be inherently convoluted in all of this.
I think there are places where I can have a cake and eat it too. So for example, Adam Chipala's work on generating these cryptokernels in there, it's done in a very formal way, correct way, but they get fastest cryptokernels out there that's used in all cryptocurrency systems right now. So you can have both ways.
Yeah, bouncing on what Chen was saying, I think you can also allocate a cake and eat it too in a different way, a different dimension, by saying sometimes you want to opt out of some performance optimizations. It's the case in hardware for side channel attacks, for example. And we want it also in compilers. Actually, the analogy is with debugging. So in general, being able to trace down information from the source language or whatever source description down to some intermediate level and even further has been the challenge. When you optimize the code, we don't even have a robust way of doing that in general. We have more like best effort ways of conveying like even source line information down to all of the code. If you want to address security aspects like physical security, like microarchitectural state, any information like Spectre that is not visible at the ISA level, you first have to solve that problem. I think we are still very far from having good traceability mechanisms in compilers, and it should go both ways. It should also like type systems are great for programmers, but we should go beyond that. How to expose information that the programmer can understand, or upstream passes can understand about what happened underneath. And so like this kind of two-way communication in compilers has always been the poor child of compilers. And security is definitely one motivation for progressing.
All right, excellent. Oh, we have two. So we have actually can only probably ask one question. They don't have lots of time left. Yeah.
So there's been a lot of kind of discussion about the relationship between architecture and compilers, and a through line of a lot of it has been that architects do whatever they want and compiler people have to respond to that. So I'm curious what you guys think about the future of that. Do you think that that is fundamental to a computing community that cares about performance above all else? Or do you think that's something that's subject to change over the next 20 years?
I will answer. Don't get what happened at ITAM. That ITAM system will describe why architects first compiler paper. I'll say that as well.
I think it's the architect's fault.
No, it's the facts. It's the Intel thing. I mean, anything was the greatest thing. It's the slave brand. It's just that we didn't put the right technology.
But I want to make one comment on that. Maybe so I didn't say architects do whatever they want. I think they do whatever fixes the problems that the compiler people didn't fix. I think underneath of all of that is the insight that you can basically speed up the execution of the program during using dynamic techniques as a modern out-of-order execution process that's much more significantly than you can do with static analysis. I mean, there's evidence for that. There has been this Itanium processor that relied on compilers doing magical things that hasn't been that successful after all, I think.
I agree. I mean, the very short point, I mean, hardware is more flexible than software. That's maybe paradoxical, but so it's the blame is on the software side. We need to accelerate. We need to be able to develop new compilers, new frameworks, or at least evolve them much faster so that architects don't have to play this guessing game, or there is no like hardware roulette or whatever. We need to be able to be much faster at adapting at whatever ideas, like including design space exploration. And I mean, it has been in the air for a very long time, but we are not there yet. Way too slow.
If you haven't heard of thing called Probstein's law, Google Probstein's law.
That was a pretty optimistic one.
Yeah, I want to like what Albert said repeatedly. It's really we want to find out what's the right use of the compiler technique we use it where it's best at. But the question is what something is. To take a concrete example that Sebastian said, extracting kernels or run on accelerators. That's actually one of the feedback I get from my colleague Michael Scott. So is that something that you think is compiler good at or not?
Extracting kernels?
The wrong accelerator.
Depends where you start from. Well, starting from C, no. I'm not good at that.
All right, Mary, you have something, right?
It's okay. Go ahead.
All right, okay, so regarding time, we have only 2 minutes left. So I'm going to summarize the discussion. So I have talked a lot. 1 hour, I mean, very impressive. So the summary will be very brief. I only found out several keywords I heard again and again. So one keyword is automation, automating compiler construction, making compiler easier for developers to use, to create. And then second is about the data. So data actually is essential. Well, we talk about machine learning, AI, we did not really dive deep into that. But one important thing for using this technology is about the data. So someone has an excellent point, put it on the cloud, then we can collect the data automatically in a larger scale. So, and then the other one is about actually formal specification. This actually came up again and again as well. This actually, I feel like this is a fundamental challenge to compiler because well, compiler, we have lots of ways to analyze, to inference, but if well, the main barrier is, well, can we understand what this program is about? This is understandability, formal and also hardware models as well. Now, this is important. If we have these suspicions, then we have to do a lot of things. But the problem in reality actually is very hard to get here. I did not hear a lot from panel how to address this problem, just heard lots of arguments about the importance of this. Now, there's some other aspects mentioned about memory, data locality. These things are critical in the future as well. And also some kind of synergy with, and also maybe two-way relations with security, privacy. Now, productivity is also important to mention. We did not dive deep into it, but I think that actually is something. If we can use AI in a good way, that is something welcome. So that's my summary. And then before we thank our speakers, our panelists, actually, in my preparation, I also invited another excellent ChatGPT. I asked the ChatGPT this question. So here are the answers. So continue focus on optimization.
Did you provide any context before? It was just the first question.
This is the first question.
Because that influences a lot.
Right. So and then second is the integration of AI ML techniques. Third is increase the focus on security, greater support for new programming languages, improve the support for parallelism, increase the use of domestic compilers, increase use of heterogeneous architectures, greater focus on energy efficiency, increase use of machine learning for code generation, increase use of automated testing, more focus on portability. I said, well, next I said, well, wait a second, sorry. After this, I said, well, more exciting prediction. Compiler that can understand natural language. AI-powered compiler that can automatically optimize code. And then compiler that can optimize for user preferences, compilers that can automatically generate code here actually based on high level specifications or natural language input. And then quantum compilers. All right, so well, let's thank all of our panelists.